Okay, so we've got two guitar strings of equal length but of different thicknesses, and they're under the same tension. The strings are made from the same material. The thinner string has a diameter of 0.20 millimeters and the thicker string has a diameter of 0.80 millimeters. We've got to find out the value of the ratio of the elastic potential energy in the thinner string in comparison to the elastic potential energy in the thicker string. Okay, this one is a little bit convoluted, but we'll get there. This is certainly the kind of question I'd recommend. This is why you do your multiple choice questions last, because for 1 mark this is a lot of work. So let's get to it. Let's have a nice blue colour there. Right, so what I'm going to start off by saying, well, we know that they're the same material, so they've got the same Young modulus, and the Young modulus is stress over strain, and stress is equal to the force over the cross-sectional area, and the strain is the ratio of the extension to the original length, and because I'm dividing by the strain, that's multiplied by 1 over it. So if I multiply by the original length and divide through by the extension, I get that. Right, my thinner string I'm going to call here string number 1, and I'm going to say over here we've got string number 2. Okay, the important point, let's deal with the areas to begin with. String number 1 has a diameter that is 1/4 of that, and because the area is proportional to the diameter squared, what that tells me is the area of string 2 is going to be 16 times the area of string 1. Okay, now if we come back to our original equation, because these two are both going to have the same Young modulus, I'm going to equate these two together. Now, they've both got the same force, and they've both got the same original length. We're going to have area 1 multiplied by the extension of number 1, and that's going to equal the force times the original length over area 2 times by the extension of number 2. Now, because they've both got the same force, that will cancel. Because they've both got the same original length, that will cancel. So that tells me I've got 1 over area 1 x1 is going to equal 1 over area 2 x2, and therefore if I flip those on their head, I can just say that a1 x1 is going to be the a2 x2. Now, earlier we showed that area 2 is going to be 16 times the area of 1, so let's put that into here. So I'm going to have a1 x1 is going to equal 16 times a1 x2. I can cancel off this cross-sectional area now, and what that will tell me is now that extension 2 is going to be 1/16 of the extension of 1 of the thinner string, which is what we'd expect. So the thicker string is extending less under the same force. Okay, now we've got to look at the elastic potential energy. So that I'm going to be using, as I don't know anything about the spring constant, and that's going to be a long route to get to that, so I'm just going to say it's going to equal 1/2 Fx. Now, the thinner string is string number 1, so if we put that in, so we're going to have Fx1, the extension number 1, over 2, and then that's all going to be over F x1 over 16, also divided by 2. The 2's can cancel off, the f's can cancel off, so that's going to leave me with, well, let's just put these in. x1, make it a bit neater. x1 over 16, that's the same, well, the x1's cancel, so that's going to be the same as 1 as being 16. So our answer is D, 16.